Welcome to AP Chemistry at Honolulu High School. I'm Brian Brown, and today we'll be looking at extra help for the Chapter 13 test. And these are some of the common errors and misconceptions that we'll be looking at in this set. Now, first one, watching units. Remember, this is a key component to pretty much every single chapter. Big thing here is always know when you're talking about mass or moles or liters of what in a problem. So are we talking about of solute, of solvent, or solution? When you look at all of our different concentrations that are in the chapter, they're all specifically tied to a very specific thing. Make sure you understand whether it's the solute or the solvent or the solution. So be careful of units as it relates to that idea. Next one, different types of concentrations. When you're looking at um, mass concentration versus mass volume concentration. So we're looking at our different types of concentration here. So all of these are different types of concentrations. Which one of these are specifically related to mass? And which ones of these are specifically involving a volume? Well, percent by mass, part per million, part per billion, mole fraction, which is the chi here, and molality, every one of those things involves mass and moles, which means they're all mass type calculations. So when you're doing these calculations, it's all about finding the mass of the solute and finding the mass of the solvent. Because if you find those two things, you know the mass of the solution and that relationship. So these are all molar mass conversion and mass of solute plus mass of solvent equals mass of solution type problems. Now, the other style of problem that we have over here is this one. And while on top we do have moles of solute, which is related to mass, on the bottom this is the only time that we really have a volume. And notice it's the volume of a solution. So all of the ones on the left are mass concentrations, and the one on the right is a mass volume type concentration. Now, out of all these concentrations, one thing you should also understand is which ones of these will change with a change in temperature. Well, mass, and every one on the left is mass, is totally unrelated to temperature. If you change your temperature, it does not change the amount of substance that you have. But this one has a volume in it. And most substances, when you heat them up, they expand. So molarity actually changes with the change in temperature. So out of all these, molarity is the only one that's temperature independent. So that's why when we're doing some of the colligative property calculations, like boiling point elevation and freezing point depression, we're dealing with changes in temperature. Notice molarity is not in that equation. It's molality that we use in those situations, and that's why, because molarity is temperature dependent. Next situation here would be dealing with different types of solubility questions. So it might be something like, what will dissolve in, or what is more or less soluble in, or arrange these from most to least soluble in. Well, in all these situations, we're looking at really different things related to solubility. And our key idea for that is like dissolves like. And remember, what we really mean is polar dissolves polar and nonpolar dissolves nonpolar. So that's really what you have to identify. Are the substances polar, or are the substances that we're looking at nonpolar? Or I should specifically say, is the substance we're looking at polar and nonpolar, and how do the other things compare to that? Because remember, the more like it is, the more soluble it's going to be in it. The less likely it is, the less it's going to dissolve. So learn to recognize some polar and nonpolar things. Now our nonpolars, things that should jump out at you. Whenever we have a gas, so any gaseous substances, including gaseous elements, think of those as nonpolar things. Gases are dead giveaway that at room temperature it's not strongly held together. That's nonpolar. Diatomic molecules are Hahn-Fickelbrei diatomics. All those are gases. All of those are held together by nonpolar polar forces. Look for perfect symmetry, like our tetrahedral, XBr4, CH4, those types of things. Always look for different types of perfect symmetry things, including something like CO2, which we've run into a number of different times. Remember, this is a perfectly symmetrical carbon with two oxygens coming off of it. So if you see a formula and you're not sure, draw it. It's one of the reasons why Lewis dot structures comes before this chapter. So there are certain types of things you should start to recognize by shape that are going to be nonpolar. And then finally, remember hydrocarbons, always nonpolar. Whenever you see hydrocarbon, first thing that should pop in your mind is nonpolar. Now, as far as the polar things, look for your non-symmetrical molecules. Some of those will jump out at you, some of them won't. You may have to draw it. Look for binary molecules that are, and as a binary molecule, that means two things, and they're not the same thing. Well, With this simple binary two atom situation here, unless they're the exact same thing, or carbon and hydrogen, they're probably going to be polar because the electronegative difference is going to be great enough. So look at our simple two atom binary molecules. Those are typically going to be polar things. Watch out for acids, strong and weak, and so forth. And watch out for hydrogen bonding. You need to look at situations because they often slide into the polar discussion when you have hydrogen bonding, because remember that makes a higher level of attraction if you've got a hydrogen bond type situation. So water, ammonia, alcohols because they have the OH in it, carboxylic acids because they have the OH in it. All those are things that are going to display hydrogen bonding, so look out for them. And remember with our complex molecules, you may have a polar and a nonpolar component. And then it's all about how big is the polar versus the nonpolar component. Because if you have something with a relatively large nonpolar component compared to its polar component, then this is going to be more attracted to nonpolar things and less attracted to polar things. If, on the other hand, you have a relatively small nonpolar component and an equal or larger polar component, then this is going to be more attractive to something that's polar. So the length of that hydrocarbon chain, because that's really usually what we're looking at here, makes it a bigger and bigger and bigger non-polar component. So also recognize when we have complex type molecules that contain polar, like hydrogen bonding, and non-polar, like a hydrocarbon component. So those are our like dissolves, like such solubility situations. Next thing, biggest change in the colligative property. People often struggle with this. Remember, you have to take into account when you're looking at how much a colligative property changes, it's really about the total number of dissolved particles. So it's not just the molality, it's also the I value. So you need to look at how much we've got in terms of the concentration, and you need to also incorporate in if this thing is ionic and it has an I value greater than 1. So remember, if this gives you a larger term, when you multiply those two together, it's going to raise your boiling point more, lower your freezing point more, affect your uh, vapor or osmotic pressure even more, affect your vapor pressure even more. So make sure you're incorporating in both when you're dealing with how much a colligative property changes. Next, molarity to mass concentration conversions. Now you've looked at these in a couple of different situations, so I'm not going to go through and redo a problem. You can find a problem in your book, but I do want you to recognize there's three components that you need to take into account. First and most important, massive solute plus massive solvent equals the mass of the solution. That's a critically important component because sometimes we're dealing with massive solvent, sometimes we're dealing with masses of solute, sometimes we're dealing with massive solution. And you need to understand that if you know two of these three, you can always solve for the third. Second thing, because we're going from molarity, which is a volume situation, to any mass concentration, or vice versa, you need to understand the bridge that density represents. If we know the mass of the solute and the solvent, we know the mass of the solution. If you are given the density, we can use that to calculate the volume of the solution, which is what we need if we're calculating molarity. So getting the moles is no big deal, but getting the volume is usually where people struggle. Understand that this relationship is how we would get that volume to plug into there. And if you're given molarity, realize that if you know the mass of the solution, or I should say, if you know the density and the volume of the solution, you can solve for the mass of the solution using this equation. So going the other direction, you can do the same thing. And then finally, start the problem by writing the given concentration as the fraction it actually represents. So if it's 2.2 molar, make sure you understand and write it as 2.2 moles over 1 liter. And remember, that is solution and that is solute. Write it out no matter what it is. If it's a mass percent, write it out at 12%. 12 grams of solute over 100 grams of solution. So make sure you write it as the fraction it represents, because seen this way, you're going to see a lot more information that's going to be useful to you for this type of problem. Now, the last situation here, for whatever reason, people tend to struggle more with Raoult's law because I think it's the first one we looked at, so it's a little bit older, and it deals with mole fraction. And while we have done that now a couple of chapters in a row, for whatever reason, people struggle with this idea. But the key to Raoult's law is understanding it has to be the mole fraction of the solvent. That's really the key to mole fraction problems. Calculate the mole fraction of the solvent, not the solute, and multiply it by the pure vapor pressure. And this ends our test help movie. I hope this helps you get ready for tomorrow's test.